Good morning, everyone. My name is Jeong, the presenter of our paper. The title of our paper is Depth Extraction from a Single Image based on block matching and robust regression. So, contents of this presentation are like this. At first, I'll show the necessary of 2D to 3D conversion, and then I'll introduce some related works. And I'll explain our proposed method with some experimental results. Finally, this presentation will be finished with some conclusion. So, over the last decade, we can observe a massive advance in 3D capable hardware such as 3D TV, gaming console, or smartphone. However, 3D content production still remains a challenging task. They are usually produced by labor-intensive, which are time-consuming and expensive tasks. So, to make abundant 3D content, it is essential to convert existing 2D contextual scenes into 3D. So, the 2D to 3D method can be divided into two groups, semi-automatic and automatic method. Semi-automatic method expects user interaction such as depth scribble. The unknown that pixels are filled by propagating the scribble. However, they are not suitable for automatic vision tasks. On the other hand, automatic method does not expect any user interaction. For example, traditional automatic method extract depth map using monocular cues such as shading, motion, or defocus. However, the performance of their results are highly dependent on their restricted assumptions, so they are not suitable for general situations. Nowadays, after the emergence of large RGBD datasets, learning-based methods are receiving lots of attention. Among them, we focus on the non-parametric sampling approach to 2D to 3D conversion. Now I introduce some related works. The first attempt in non-parametric approach is depth transfer. In this method, visually similar scenes are retrieved from RGBD dataset using gist feature, and warped candidates are obtained by calculating shift flows. The final inference depths are obtained by solving optimization problem using this warped candidate and input images. However, calculating shift flows and solving the optimization problem is highly computational, so it's very slow. The another method in non-parametric approach is depth fusion, which does not perform any global warping process. In this method, the final depth map is obtained by obtaining the median values in each pixels in retrieved image. So it can implement it in real time. However, it might fail to assign proper depth estimate to the region where candidate scenes are not closely matched to the input image. Another non-parametric, contrary to the previous method, this depth analogy method extracts depth gradient field rather than depth map directly. So it can extract very plausible depth gradient map, and to obtain the depth map, it obtain this depth map by solving the Poisson equation using this estimated depth gradient field. However, in this reconstruction process, it is hard to assign proper boundary conditions. So, yes. Now I tell you the difference between our method and the related works. Comparing with depth transfer, we reformulate the global warping process as simple block matching and regression problem, so our method is much faster. And compared with depth fusion, we consider the geometrical configuration in the whole neighborhood so we can obtain robustness in fusion process. Finally, we obtain depth map directly rather than obtaining depth gradient like depth analogy. Now I'll explain our proposed method with details. In our method, we assume that visually similar scenes also have semantically similar 3D structures. So we retrieve visually similar scenes from RGBD dataset using CNN descriptor. For efficient retrieval, the descriptors for all images are pre-computed, and the visual similarity are measured by this equation, and the lowest K candidates are retrieved from dataset. So actually, the CNN descriptor is the output of the hidden layer of this AlexNet, which is 4096 dimensional. And also, it is known that the CNN descriptor outperforms handcraft features like shift to describe images. In the experiment, I showed the retrieved image by CNN descriptor comparing with conventional gist feature. For depth inference from the retrieved candidate images, we group depth samples via block matching, resulting in K-depth samples. In this figure, blue rectangles in input is a patch centered the red point. Also, the blue rectangles in these candidates are the result of block matching using shift feature. We obtain these patches by KD3 algorithm. So the 3D volume patches are constructed by stacking these patches. And from the 3D volume patches, we obtain the final depth patch by solving this regression problem. In this equation, the W denotes the weight measured by the block matching cost these shift features. We solve this problem using iteratively related least scale algorithm. And after processing all the patches in input query, there exist overlapping patches, so we obtain the initial depth map by averaging them. The initial estimates still noisy and are not aligned with the boundary of the input query, so we refine this initial depth map using joint weighted median filter. In this process, we use texture smoothing image as guardians rather than input image directly, so we can avoid the texture copying problem frequently occurred in joint filtering techniques. Now I'll show the experimental results. The experimental setup is shown in here. And the performance of our method are determined by this normalized cross covariance in this equation. The higher C-score indicates higher correlation to the ground truth. And in our experiment, we use this two RGBD data set, make 3D outdoor data set, and NIO Kinect V2 indoor data set. We divide the testing and training set as shown in this table. This figure shows the retrieved image by CNN descriptors comparing with the conventional gist features. As you can see, our result is more visually similar with input query rather than using gist feature. Furthermore, the initial depth estimation is much better than this CNN result. And this page shows the impact of texture smoothing in depth refinement. When we obtain the depth map using the input image as a guidance directory, we can confirm that the texture copying problem like these red and blue rectangles. However, we use the texture smoothing image as guardian, so we can handle this texture copying problem as shown in these figures. In this figure. And this page shows the result of our proposed method with competing algorithm, depth transfer, depth analogy, depth fusion, and make 3D algorithm. You can confirm that our result is more plausible. Our method find more plausible depth map comparing with the competing algorithms. And this table shows the quantitative evaluation with competing algorithm. Our method received the best average C-scores comparing with other methods. Although our method is much slower than this depth fusion method, as you can see, our method is much better depth map result. And this figure shows the Z-scores with the indoor scene with comparing algorithm. In these figures, we can also our method received the best scores with comparing with the other algorithm. Now I finished our presentation with conclusion. Our method is the first attempt at CNN descriptor of non-parametric sampling framework. And we propose a robust candidate fusion method which considers the geometrical configuration in a whole neighborhood. And finally, by the effective refinement method, we can resolve the texture copying problem frequently occurred in conventional approach. Thank you.